All right, let's go ahead and start chapter 3. We're going to start with section 3.1. We're going to learn some terminology about probability. All right, well, probability is the measure that is associated with how certain we are of outcomes in a particular experiment or an activity. An experiment is a planned operation carried out under controlled conditions. If the result is not predetermined, we call it a chance experiment. So, for example, flipping a fair coin one time or two times or however many times is a chance experiment. Few more vocab words. The result of an experiment is called the outcome, and a sample space is a set of all possible outcomes. We can represent sample spaces in many different ways. We can just list them. We can draw a tree diagram. We can create a Venn diagram. And we'll be mostly listing them in this section, but we will talk about the other two later. We usually use the uppercase letter S to denote the sample space. So for example, if we flipped one coin, S would equal the set H or T, where heads or tails are the possible outcomes. An event is any combination of outcomes. We use uppercase letters like A or B to represent events. For example, we flipped one fair coin. A might be the event of getting at most one head, and the probability of an event is written P of A. The probability of any outcome is going to be the long-term relative frequency of the outcome. I'll talk about that a little bit more, just hang on there. Let's talk about some things about probability. For one thing, it has to be between 0 and 1 inclusively. You can have a probability of 0, meaning no chance that this can ever happen. A probability of 1 means it will always happen. And a probability of 0.5 means it's just as likely to happen as it is not to happen. So let's look at what we mean by probability. Let's talk about what we mean about probability. Let's say we flip a fair coin one time over and over and over again. As we do the experiment more and more and more times, that probability is going to reach a half. Just for fun, let's look at a little website here. This will pop up in my window. This is a fun one. Oh, it's coming up in a different window. Hang on, I'm dragging it over here. So here's a fun website. It has this fun box of global statistics here. And there has been, 16 million total flips of the coin. Let's add another one to it. And it was recorded all the times people have come and flipped this coin, right? And if you do it a couple times, that number will go up as well. And you can see after 16 million flips, 50.01% of the time it's heads and 49.99% of the time it's tails. So even after 16 million flips, it's still not exactly at 50%. But if we did this forever, infinitely many times, that would reach a half. And that's what we're talking about when we're talking about probability. All right. Equally likely means that each outcome it would occur with the same probability. So for example, let's say you just roll a fair six-sided die. Each face has 1, 2, 3, 4, 5, or 6, and each face is as likely to occur as the other face. If you toss a fair coin, heads or tails are equally likely to occur. Or if you're taking a true-false exam, you're equally likely to be right if you pick true or false. In this situation, we can calculate the probability of an event. What we do is we count the number of outcomes for the event and divide by the total number of outcomes in the sample space. Let's start with an example of tossing 2 coins. What is the sample space if we toss 2 coins? Let's write it out as a set. So here's my sample space S. It's equal to heads, heads. That's heads on the first, heads on the second. Tails, then heads, heads, then tails, and tails, and then tails. Those are the 4 possible events that could occur in my sample space. Nothing else could happen. Okay? Let's have event A be the probability. Let's have event A be the event that you get exactly 1 tail. What are the set of outcomes for event A? Let's write it out. And how many events? After you've written it out, you'll know how many outcomes there are at event A. Event A will be heads, tails, or tails, heads. That's the only way you could get exactly 1 tail. And there is 2 outcomes in event A. So the probability of A is going to be the number of outcomes in event A, which is 2, divided by the number of outcomes in the sample space, which is 4, and this is equal to a half, or 0.5. Probability is one of those subjects that starts really straightforward, and you might be like, oh yeah, this is totally obvious. Of course, there's a half chance of getting exactly 1 tail. But it can get complicated fast, so I like to be really careful at the beginning. Let's try another example. Let's say you roll 1 fair six-sided die with numbers 1 through 6 on its faces. What is the sample space? I want you to pause the video right now and write the sample space out as a set. S equals, and then the sample space. Are you back? Did you get S equals 1, 2, 3, 4, 5, 6? Good. All right, let's let E be the event that you roll a 5 or a higher. Now I want you to pause the video and write out the set E. What are the outcomes in this event? All right, you back? E is equal to the set 5 or 6. That's a 5 or higher. So we can find the probability of E by counting the number of outcomes in event E and dividing that by the number of outcomes in the total sample space. That's 2 in E divided by 6 in the sample space. 2 and 6 are equal to 1/3. All right, well, let's think about this result for just a minute because it's got to keep in mind exactly what we're doing here. This doesn't mean that if you rolled a die 6 times, it would be 5 or higher exactly 2 of those times, right? That's not what this means. We don't mean if we just roll it a few times, we know that, oh, okay, we roll it 6 times, we're going to get 1, 2, 3, 4, 5, 6, and 2 of those are going to be 5 or higher. That's not what this is saying. This means that if you were to roll a die a very, very large number of times, millions of times, billions of times, overall, 2/6 of the rolls would be at least 5. We would not expect it to be exactly 2 out of 6 rolls. Just making sure we understand that probabilities are about long-term frequencies, not that if we did 6 rolls, 2 of them would be 5 or higher. You need to do a lot more than 6. All right, let's do another example. Let's use the following information to answer the next 6 questions. A jar of 150 jelly beans contains 22 red jelly beans, 38 yellow, 20 green, 28 purple, 26 blue, and all the rest are orange. First, before we jump in, does this experiment have equally likely events? Can we still compute the probability using the number of items in each event divided by the total? I want you to pause the video and think about this for a second. Does this experiment have equally likely events? All right, have you thought about this a little bit? The answer is no. It doesn't have equally likely events. You're more likely to draw a yellow one than you are a green. There's 38 yellow and only 20 green. So they don't have equally likely events. And the answer to the second part of this, the second question is, can we still compute the probability the same way? The answer to that is actually yes, we can. And the reason is, the reason I like to think in my head is if I went in and I labeled each jelly bean, right? I labeled the red ones, red 1, red 2, red 3, da 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 da. I label the yellow ones, yellow 1, yellow 2, yellow 3, up to yellow 38, etc. I could make E be the event that you draw a red jelly bean, and E would have all 22 members, R1, R2, R3, up to R22. So if I designate it that way, each individual jelly bean is equally likely, so I can't compute the probability the same way. Let's go ahead and try to compute some probabilities with this guy. All right, pause the video and answer these 6 questions, please. Probability of getting a blue, a green, an orange, a purple, a red, and a yellow. You might have to do a little bit of math. All right, are you back? Did you get the same answers as me? 26 out of 150 are blue, 20 out of 150 are green, 16 out of 150 are orange. We did a little subtracting for that one. You took the 150 and subtracted up all the other ones to figure out that there was 16 orange. Purple, 28 out of 150, red, 22 out of 150, and yellow, 38 out of 150. All right, good start on probability here. Let's keep going. Let's talk for just a moment about probabilities for outcomes that are not equally likely. We did the jelly bean example, and that one we could sort of force into our normal way of computing probabilities. But let's think about an example that doesn't really work that well. So let's say that a particular neurosurgery is successful 85% of the time, or 0.85. If we want to find the probability that 2 knee surgeries are successful, we can't just count, right? So in this example, the sample space would be successful, successful, success, fail, fail, success, fail, fail, right? But each one of those do not have equal probabilities, right? We cannot say 1 out of 4 of getting 2 successes. That's not the way it works. So we're going to talk about this later, but I just wanted to forewarn you that you have to be kind of careful when you're dealing with probability. All right, let's talk about the word or in probability. If we want to know A or B, that means we're looking for the outcome that is in the event A, or it's in the event B, or it's in both A and B, okay? And this gets a little confusing because we talk about and later, so let's do an example. Let's say A is equal to the set 1, 2, 3, 4, 5, and B is equal to the set 4, 5, 6, 7, and 8. If we wanted to find the event A or B, it would be all the events in A, 1, 2, 3, 4, 5, and all the events in B, because it's in A or it's in B, 4, 5, 6, 7, 8, or any that are in both, we don't list them twice. So if it's in A or B, that it's in one or the other, or it's in both of them, okay? So that's A or B. Let's do an example using our jelly beans. Let's let B be the event of getting a blue jelly bean, and R be the event of getting a red jelly bean. What is the probability of B or R? How many outcomes are going to be in B or R? Pause the video, write it down. All right. Did you come up with what I got? The probability of being B, there's 26 in B, and there are 22 in red, and we have 48 of those total out of 150. So the probability of being blue or red is going to be 48 out of 150 or 8 out of 25. Let's talk about the word and. An outcome is in the event A and B. If the outcome is both in A and B at the same time, it must be in both of them. For example, if we use our A and B from before, A is 1 through 5 and B is 4 through 8, the events A and B are 4 and 5 because they're in A and they're in B. Let's try this for an example. Let's think about rolling a fair die 2 times. Think about what our sample space is here. It's our sample space, right? I wrote it all out for you so you can easily look at it. Let's say A is rolling a 1 and B is rolling a 5. What events are in A and B? All right, well, let's think about this. A rolling a 1 would be any of these guys, right? Those all roll a 1, but so does this one, this one, this one, this one, and this one, right? Those are all the events at A. I wish I could change the color on this. I'm sure I can, but I can't figure out how to do it. Let's let B be rolling a 5. All right, so what's in 5? I'll underline those guys. Well, these all have a 5 in them. They did in this? Yeah. Here's my 5s. These all have a 5. So do these, and these. All right? All have 5s in them. So what we need to think about now, maybe I'll draw boxes around the 5s instead of make it look nice and square. Box around the 5, around the 5. All right, so for it to be in A and in B, it both has to have a box around it because it has 5, and it also has to have a circle around it because it has to have a 1. So there's this one, I'll draw a big circle, and this one. Those are the only 2 that are in both A and B. Okay? So the probability of A and B is going to be 2 chances out of 36. All right? So I wrote it all out here too. So A is equal to all these guys, and B is equal to all of these guys. A and B is equal to 1, 5, or 5, 1. That's the only 2 ways you can roll a 1 and a 5. So the probability of A and B is 2 chances out of our 36 total chances, which is 1 out of 18, which is approximately equal to this decimal. All right, let's learn one more new term. It's called the complement, and it's writ A with a tick mark, and it is read A naught. A naught consists of all the outcomes that are not in A. All right? If you add the probability of A with the probability of A naught, you always get 1. Let's talk about this for just a second. Let's let our sample space be a rolling a die, 1 through 6, and our event A is rolling a 1, 2, 3, or 4. In this example, A naught, things that are not in A, are 5 and 6. Okay? And let's think about this statement here about how the probability of A plus the probability of A naught is equal to 1. really what we're saying is the probability that the event occurs plus the probability the event doesn't occur is always 100% of the time. So it either does occur or it doesn't. There's no other options. That's really what that equation is telling you. And if we look at down here, the probability of A occurring is 4 out of 6, 4 chances out of 6. The probability of it not occurring, 2 chances out of 6. And so it either occurs or it doesn't occur with 100% probability. That's it for section 3.1.